You've gone swimming, hopefully, and forgot to get out, and your fingers ended up, whoa, fingers ended up looking like this. Right? Did water go into your body or out? Why does it look so puffy looking? It went into? Everybody agree? In nature, what does stuff like to do, Alyssa? Does stuff like to travel from regions of high concentration to low concentration? Or is it natural for stuff to go from low concentration to regions of high concentration? Yeah, that's what's natural, is high to low. Like, take some concentrated mixture and drip it in the beaker of water here. You'll see it just disperse, right, from region of high to low concentration. So that's what's natural. So the question you have to ask yourself, where's the water more concentrated? Jasmine, is it in that swimming pool or is it in Tegan's finger? Tegan's finger has more pure water than what's in, well, what I'm getting at is, because what's in her finger? She's got blood, she's got bone, she's got a lot of weird stuff in there. I'm not a biologist, but there's a lot of stuff in you. But Star Trek says you are essentially walking bags of water. So that's true, but you have a lot of other stuff in there. The swimming pool, it's not pure, but it's a lot closer to pure water than what's inside Tegan's finger. So the water is actually more concentrated in the swimming pool. You can take the concentration of anything, right? Big M, molarity, is moles over liters. And if you take the moles of like a big bottle of water, the swimming pool, you plug in the number of moles, you plug in the number of liters, and you always get the same answer. Pure water is about 54.4 molar. So I'm not saying the swimming pool is 55.4 molar, but it's pretty close. So it's more concentrated on the outside. So it travels into her finger. So when she was done swimming, she gained weight or lost weight? Gained weight, water weight, but everyone says that's a good thing, right? Okay. Fixing wilted lettuce. They put the lettuce in what? Probably. Water, cold water. Takes 3 hours, but you know, I don't have to throw that stuff away. I throw it away, but I don't want to wait 3 hours. Okay. You've probably heard of dialysis membranes, or if you're in biology, you might have bought some of this stuff, right? And it just looks like cellophane, and there's little tiny holes in it. And you can buy this stuff so that the little tiny holes match whatever you're trying to mess with in your system. Like you have bacteria that, you know, the holes are a little bit bigger on the sides of micrometers, like a hair, or go like 1,000 times smaller, and you start talking about glucose or vitamins, right? Make the holes a lot smaller. So let's take a look at what's going on here with osmosis. So what I'm going to do is here's my membrane, and I'm going to shoot in a bunch of little particles on the bottom. Put a few up on top. Okay. So this membrane, there's no holes in it, so I need to put some in there. But the solution appears more concentrated where, Crystal Munoz? On the bottom, obviously, right? So this could be sugar, it could be salt, it could be that virus they're talking about. Okay, let's put some holes in there. Holes that are big enough to allow this stuff through. Okay, now it goes both ways, though. You can't stop it. But if we sat here and waited long enough, Jarixa, what would happen? Would it all end up on one side? Would they just even out? They'll just even out, right? And right now, I mean, it's getting closer already. But it'll even out if you wait long enough, okay? But you can't stop it going both directions, okay? So if this is, and this whole thing is, this is osmosis. I think diffusion, same thing, but osmosis, it's going through a semipermeable membrane. Shoot some more in here. Okay, I want to do reverse osmosis. Let's say these little diamonds are salt. And I want to do reverse osmosis to get this nice pure drinking water. Right? I'm out there in the middle of Saudi Arabia and I can't drink the ocean water or whatever, but hey, I can do reverse osmosis. What's reverse osmosis? Thinking about this. No. Evaporating is going from liquid to a gas. You could. That's one way I could get the pure water. I could evaporate it all, then have to collect it, and then just condense it down again. But no, I've got money, man. I'm Saudi Arabia. I'm going to put some electricity into this and just pump out pure water, doing reverse osmosis. What could I do to this system to get pure water on one side? I don't want to close the gates. What I want to do is apply a whole bunch of pressure. Because remember, what can go through here? Only sodium ions and chloride. Water's not going through, not for these holes. These holes are so small that only these little ions can fit through. So I'm going to apply a whole bunch of pressure on top. And it's just, right, reverse osmosis. It's going to push the ions through there, and I'll have pure water up on top. Okay? So we're not talking about reverse osmosis, though. We're just talking about osmosis. Here's another example of osmosis. You have a little snail, Sabina, he's running around on your little sidewalk, and some evil idea enters your head. So you go grab some salt and you sprinkle it on the little snail. You see all these little bubbles on him. Water's going into or out of that snail? Out of, right? Because first the snail's all hunky-dory, right? But once you dump salt on him, the concentration outside of him, the water, he's all wet, right? The concentration outside of him is just dropped like a rock for water. So water just comes out of the snail. All right, that'd be a horrible way to die. Right? Okay, I assume snails feel pain. Oh. What is osmotic pressure? Here's another animation.
When two solutions with the same solvent are separated by a semi-permeable membrane, solvent molecules migrate through the membrane from the solution of low concentration to the solution of high concentration. A concentrated glucose solution is added to an inverted funnel with a semi-permeable membrane, and the funnel is placed in a beaker of pure water. Water flows from the beaker into the funnel. The upward flow of solvent stops when the pressure of the solution above the membrane equals the osmotic pressure, pi.
Okay, so take some water. Fine, right? Put some water inside here. The magic happens at the semipermeable membrane, right? So I got to put a membrane on here that only, in this case, water can fit through. I'm going to have sugar or something dissolved in here. It's bigger than water, so it can't fit through the little holes. Okay, so I'll have water in this part, dissolve some sugar, right? Put it in here. Water's more concentrated where? Outside, so it wants to travel inside. You can't stop it. So it travels inside. But you can stop it, right? The level's just going to keep coming up, coming up, coming up until the pressure, there's some pressure with osmotic pressure. That's what we're trying to get at. If these little water molecules want to go inside, that's pressure. It wants to go from here inside. So if you apply a pressure, maybe put a balloon on here, fill it with air, right? So it's applying a pressure this way. It will stop the water from coming up. If you apply the pressure too high, it's going to force the water out. It's going to do reverse osmosis. That's too much. We just want to stop it. So the pressure that you're going to exert is the osmotic pressure. That would exactly stop that liquid level from going up. If you don't apply enough osmotic pressure, it's just going to keep coming up until it reaches the osmotic pressure. How do you generate pressure? What pressure is out here in the first place? Atmospheric. So this is in here. You have atmospheric pressure pushing down on this thing. But then if you have a column of liquid, you have atmospheric pressure plus the column of liquid. So that column of liquid is the osmotic pressure that they're talking about in this diagram. Okay. So we have one more colligative property to worry about. That's osmotic pressure. Whoop, I skipped the equation. Let's take a look at this equation first for osmotic pressure. Let's start with R, though, because we want to figure out what the units are for everything. We've seen R before. Vivian, where have we seen R before? Yes, it's a constant. The what constant? Ooh, it's 0.0. It's the... All right. Now, where is all this useful information?
In this paper that you get.
On that cheat sheet, right? What is it called? The what constant? It starts with the G.
Yeah.
The gas constant. Okay. So that's what R is. 0.0821 liters times atmospheres divided by moles and kelvins. So, Gabby, I think R determines the units of everything else. That's your only hint I can give you. T is what? Probably temperature, and it's going to have to be in what units? Kelvin. How do we get Celsius into Kelvin again? Crystal Zamora? At 273, perfect. Okay, we have, let's do pi next, Erica. This is pi. What does that represent? Now, what is pi? Like T is temperature. What's pi? It's a symbol for. It's the equation. This equation is for osmotic pressure. So pi is our osmotic pressure. What units had that? Will that be in, Diana? ATM. Perfect. Only one variable left, and that's big M. Danny, you can figure out what big M is if you see what units are left, but what is big M? Moles, and what else is left? Liters. Big M is moles over liters. What did we call that? Molarity. We called it molarity. Right? Moles over liters. Okay. So it's just another one of those colligative properties. It's getting bigger now. I'd have that equation sheet out because look at this. We've seen some of these before. We've seen vapor pressure lowering, boiling point elevation, freezing point depression. But now we've got this whole new column. Ionic solids. What's been introduced, Alyssa? What's different? Now we have a little I to worry about. Okay. Ionic solids, molecular solids. How do you tell the difference, Crystal Munoz? Metal. You always see a metal with which type of solute? The ionic. Perfect. You've got a metal. If you see a metal, you know it's got to be an ionic compound. Okay. So then you have to use the ionic solute equation. Still doesn't tell us what little I is. Teresa, you have potassium sulfate, K2SO4. That means you better use this column of equations. We're supposed to be able to look at this formula and say what little I is. What the heck is little I?
It's either infinite
No, it's not infinity.
Or the I in math that's like imaginary something.
No. You're thinking way too hard.
Ionic. It's an ionic compound.
So,
Is it
think.
still algebra?
Yeah. What is?
What I think of is, remember how this vapor pressure lowering and boiling point and elevation, how it worked was you had these solute molecules and they were actually doing blocking, right? So really what it comes down to is the number of these blockers. If NaCl, if it didn't dissolve, if it stayed as a unit, it would just be NaCl. But it breaks up into how many things? 2. So the effect is twice as big. So they have to take that into account by introducing this little bloody eye.
So that says how much effective it is.
So little I is going to be the number of, we're talking about ions, number of
Ionic pressure.
number of ions that it breaks up into, right? The number of ions that it breaks up into. Like sodium chloride breaks up into how many ions? 2. NaCl breaks up into 2. So if you do not multiply your answer by 2, you're going to be off because it breaks up into 2 things. Potassium sulfate breaks up into how many? 3. So little I had better be 3 for that one. Okay? So it's just the number of ions. If you don't incorporate that little I, you're going to be off. Okay? So let's take a look at colloids and then we'll work some questions.
I didn't understand that definition.
For little I?
No, colloids.
Oh, colloids? Wait, okay, we'll talk about colloids. The Pepto-Bismol. There's a lot of medicines you take that are colloidal suspensions. What that means is we're used to, like when we were in the lab and we have this reaction with this reactant, make it precipitate, right? You get a little cloudy solution. If you wait long enough, the stuff collects on the bottom. So stuff should do that, right? If you have big stuff in water, it doesn't dissolve, it should come out and form a rock on the bottom. But nature's more complicated than that. Some stuff will form a colloidal suspension. Like, like milk. You would think this big honking stuff in milk would just kind of settle to the bottom because it's so big and heavy. But it doesn't. It stays in solution. A lot of medicines, they use colloidal suspensions to get solutions in your body. Plus, it looks better. If you have a colloidal suspension, you don't have all this stuff hanging on the bottom of the bottle. You got to shake really good before you take it, right? Colloidal suspension is much more homogeneous concentration throughout. So it's an odd thing. If I take one way to recognize a colloidal suspension is both of these beakers look like water, okay? This one is water. I think there might be some salt in it or something, I forget. But this one I put in coffee mate. All it is just, what? Coffee mate. But it's big molecules. It's just pretty much fat. You're dumping in fat. That's, all the water sucked out, okay? Big molecules. So if you put a laser through water, you can kind of see the laser inside the water.
Oh, I see.
But it's pretty much because of dust and things. But if you do the same laser through a colloidal suspension, you can see it really easy because those big particles, they just scatter the light. They call that the Tyndall effect. Okay. If the particles are big enough.
But it's super saturated.
But so probably
Is that what
not.
they do in chlorine?
Probably not. Because whether it's super saturated or not, the particles are the same size. So, okay. So it depends on the particle size. Okay, now we can work some questions. I'm throwing the hardest one at you first because I want to make sure we can.
So colloids are just like a brief
This little concept. You don't have to worry about it really. It's just an FYI. You can understand the world around you. An aqueous solution contains 0.296 grams of a polymeric molecular unknown compound. If there's 125 mils of solution, temperature is 25 Celsius, osmotic pressure 2.58 millimeters of mercury, what's the molecular weight of the unknown? Okay, Sabina, have you had lab yet? Okay, you had lab, that's right. So we did a question like this. All I'm saying is, what is the molecular weight? Right? Forget the whole rest of the question. But we asked in lab, what's the molecular weight? Where did we start? What's the very first thing we wrote down?
The temperature.
Do you remember?
CM
So you can remember what getting, do you see what I'm trying to drive at here? Because you can jump into equations and things, right? Like you have the osmotic pressure equation, but I don't see molar mass in that equation, right? We're after molecular weight. So start with what they're asking for. What is molecular weight? It's what over what? Grams all over moles. So if you know the number of grams of something divided by the number of moles of that same thing that those grams contain, divide the two, you'll have molar mass. So to me, this is the starting point.
So we're looking from the
Okay. Perfect. How many grams do you have here, Monica? Monica, you said you have the grams. How many do you have?
There's only 296.
No, I know your name's in them. Right? Does everyone see that? So she found half the question. The other half is going to be a lot more work, though. Okay? So we're after number of moles. Now we can write what equation, Gabby? Pi equals MRT. Now, why didn't she pick the one with an I in it?
Because she knew that it didn't have metal.
Yeah, there's no... If you use the one with the I in it, they have to tell you the chemical formula of this ionic compound. But they didn't. So you can disregard the I. However, they also said this. Polymeric molecular, right here, the word molecule. So, okay. Don't worry about I. We're after number of moles then. Is number of moles in this equation? Vivian, is number of moles in this equation? Is number of moles, can we find it in here? Because we talked about what all the variables were. I don't remember saying moles.
You take the milliliters and put it to liters.
We know R is just a constant. We know M. Use that cheat. That cheat sheet should be right next to you. M has moles in it, right? So we're going to solve for big M, then get moles, right? Here's where our moles are. So let's solve for big M. Then solve for moles. Right? Well, you could. We could. If you were good at algebra, you could do that. Number of moles, number of liters, RT. Right? And rearrange this for number of moles. That would work. But that's not how we've been doing all these problems. We've been just saying, okay, let's solve for M, and then let's set up our big M equation. So I'm just going to stick to the way we've been doing it in class. So solve for M. Do this first. Try it. Then second, solve for number of moles. Third, then you can finally find the molecular weight. Okay, try it. And everything you need is on that cheat sheet. All right? Our exam 1 equation sheet. The R is there. Yep. Multiply or divide?
Well, I thought you divided 18 by
All right.
760 to get,
So write the box. Right? Start with this. 2.85 millimeters of mercury. Draw the box. You'd see the 760 has to be on the bottom. Look right here. It's on there. There's how many millimeters of mercury in an atmosphere? 760. Right? So you got to get pi in the right units. Yeah, and you're going to have to convert that 25 into Kelvin. Right? So the conversion to go from millimeters of mercury to atmospheres on here. 273. If anyone's not sure what they're doing, just ask. Thank you. What is that called when you do that? So did I screw that up? Yeah, that makes a big difference. Bless you.
Dang it.
What's the number of liters? Does anybody get an answer yet? 10 to the negative 5? Or 10 to the positive 5? I think it should be positive 5. 'Cause I think it's going to be a big... The reason why I think it's going to be a huge number is this one word.
You're supposed to multiply it, right, on that last part?
Yeah, you have to multiply times 0.125.
Okay. Yeah, it should be. Never mind, I messed up on the...
Wait, 1 times what?
It would be something like 17.3.
1.7. Well, did you get 1.7 times 10 to the negative 5 for the moles?
Yeah, 0.194.
Okay, well, somewhere around there, right?
Do you have to put it in scientific notation?
Huh, it's a lot easier than writing 0.0000. Okay, now I'm ready for a molar mass.
For molar mass, I got 0.193.
3.296 all over 1.7 times 10 to the negative 5.
Yeah, that's what I didn't get.
Right? Yeah, around, I don't know, around somewhere around 17,000. Depending on your rounding. Did you get 17,000? Okay. Somewhere around 17,000. Yeah, it's just rounding. Okay.
Dr. Smith, okay, so when you plugged everything into the equation up there, the MWT, I mean MRT.
Pi equals MRT, yeah.
So how did you get the F over 1? Because that's what I'm
Okay. All I did is I divided RT on both sides. So this has to go over there, right? And 298 has to go over there. So I have to divide 3.39 times 10 to the negative 3, divide by 0.0821, divide by 298.
For pi, I got 0.00375.
No, you're doing something wrong.
Huh?
You're doing something wrong. Did you get...
Okay, so I had to get pi, I divided 2.85 divided by...
Oh, because someone noticed, Vivian noticed it. It's not 2.85, it's 2.58.
Oh.
Yeah, I wrote down the wrong thing too. 2.58. Okay, if you got it,
Oh, but I don't want
do number 2. If you haven't got it, let me help you out.
Can we do it on the board?
You can go to the board. Maybe we can all watch you. All right, so work on number 2. If you didn't get number 1, let me know so I can help you out, make sure you understand it. Probably. Okay. How you do number 2?
You do the IKBC.
Yeah, it's going to be this one for sure, right? IKBCM. Okay? But it doesn't really tell you. They want to know grams of sodium chloride, right? That's not even in this equation. But what is in that equation? What can you solve for? What can you get? And you can get grams out of it. Molality, right? Because molality has moles in it. Well, then you're halfway. Well, you're a lot closer than halfway. Because once you have moles, use what to get grams? What is it called? Molar mass, right? So you're going to solve for Cm. Right? And then you're going to use Cm to get moles. And then use molar mass, like Crystal said, to convert moles to grams.
And you have 2 ions.
Yeah, and your little I is going to be 2. Good. So this will be 2. And I have my book open to the KB for water. It's 0.512. Let's look this up for water. It's in the table. 0.512. What will the delta T be? 5. It's how much did the boiling point change by? So this is just 5.
Hey, where'd you get that? 0.512? What table?
I got it on page 500.
Oh, because I still didn't get that answer.
2.58 divided by 760. Okay. So you took this times this, and you bring it over here, right?
Yeah, I did it.
Okay. So that divided by that,
And I got this.
and you got 1.39. Is that what I got?
I don't know.
CM, I got
1.7.
for
No, you got
molar mass, I got
38.
times 10 to the negative 4. You're not carrying digits here. This is, yeah, you're losing your exponents.
I did. I get 1.30.
Look at that. Now, you can't use this calculator anyway. You have to get used to using mine. Well, I'll give you another one. Yeah, you got to write down that whole number. Okay.
Oh, so when I plug it in here, I use this.
Did anybody solve for this? Get grams of sodium chloride yet? 200 and some? That's a lot. I guess it's possible. How many kilograms of water? There's just one, right? Okay. What's the molar mass of sodium chloride? 58.5. So yeah, this is going to be a big number. So those lucky dudes in Colorado, if they want water to boil, I wouldn't do it by adding salt. It's a lot of salt. About 286 grams. Right? Makes sense? So with these molar mass questions, they're hard, but start out with the molar mass equation. Then you do the least amount of work necessary. It guides your efforts. Otherwise, just jump right into the equation that you need in something like number 2. Okay.
So what's the
I come.
Never mind.
Yeah. All right. So that's about it. So if you have any questions, come by. Work on it. Come by. I'll be glad to help you out.